Okay, hi everyone. Thanks for the introduction. Thanks to the COSIC team, my old research lab, to have me here today to talk to you guys about privacy-preserving computation, also known as like co-ed technologies for computing on encrypted data, or like sometimes called PETs, privacy-enhancing technologies. Yeah. So the outline of I have an hour, right, Dilara? Okay, thanks. The outline is I'm going to first introduce, motivate a bit the problem statement. I apologize if you've had some things about privacy enhancing things before in the week. I failed to do my homework on that part, so I'm sorry if I repeat some things you've already seen. But then I'll kind of go through several different methods for computing on encrypted data, like privacy-preserving computing. The idea is to give you guys an overview of what exists, what has been kind of tried in the past, what are the current sort of broad areas of methodologies, and give you guys an intuition about how they work underneath, like on the inside. But I'm not going to explain like the cryptographic algorithms and the mathematics for why these things actually work and things like this, because that I think would be a bit too deep of a technical dive, and we'd lose sight of the bigger picture. What I am going to focus on is also highlighting the different like settings or like kind of requirements, assumptions, because when we consider kind of deploying these methods, when you're writing a cryptography paper, you just say, okay, we have a bunch of parties in that want to do something. You don't really care about who these parties are, what legal requirements they have about their data, whether it can leave their system or not, and these kind of things. So I'm going to focus a little bit on what happens to the data, who can you trust to do what they say they're going to do, and these kind of things. I'm going to talk a bit about the state of the art, give you guys an idea of like how performant these technologies are today. And if we get to them, there's a few use cases to kind of exemplify, but that's not a major part. And I believe the slides will be online, so you can also just browse through them once you'll have had the context. And if anything's really unclear, we can take questions on the fly. If they take too long, I'll answer them at the end. Okay, so to get started, this talks like about data encryption, right? Cryptography kind of came out of the need to encrypt data, protect it from undesired observers, and even though we say Caesar cipher back in the Roman Empire, that was the birth of like cryptography. The kind of the simple scenario is data at rest, right? You have some data, you don't want someone stumbling on it and finding out about it. You can encrypt it with symmetric key encryption. You have the key in your head. You encrypt it, you leave it somewhere. You pick it up later, you decrypt it, and you're done. And that was kind of solved a long time ago. And of course, there's still much more to do, but the principle of it is fine. Then we have data in transit. So you can do data in transit with symmetric key encryption. You just need to one day meet the guy you're going to send a message to and give them the key. And then you can use symmetric key encryption. But the better thing that came out of the 70s and the 80s is to use public key encryption. So everybody generates a public key. Somehow you broadcast it, you put it on your blog post or whatever. And then anyone can send you messages by encrypting. Usually they'll encrypt a symmetric key and they send that to you, and then you use like symmetric key encryption from that point on. But you've solved the problem of not having to meet in the same place to exchange your secrets. And this is what TLS is based on for your HTTPS connections. This is what Signal is based on, which kind of gave the WhatsApp end-to-end encryption and stuff like that. There's still like innovations to do there, like group messaging is still a bit weird and these kind of things, but all in all, like the fundamental idea we've known how to do for almost 40 to 50 years now. The next question is, it's nice to have data and protect it. It's nice to have data and send it places. Like data in transit basically enabled e-commerce from like the 1990s onwards. The next question is data in use. Like if you want to use data, which is kind of what the big, the next revolution of like big data and analysis and statistical analysis, and then the more ambiguous, like morally ambiguous use of like online advertising and now LLM training and all of these things, that's all data in use. And so the question is, how do you maintain privacy when you want to use the data? And the question is also like, who do you maintain privacy against? So the questions that have kind of been flagging up, but that we should kind of outline, the first question is, whose data are you trying to protect? Who is the owner? Try to identify the owner of the data. What do they care about? Like, does it have to be private for them? Does the GDPR tell you have to owe them an explanation, or you have to preserve, like, protect their data for them? Then, like, who is it given by? Like, if you have a magical box that will compute on private data, who's putting the data into that box? They might not be the same as the data owners. Then who is using it? Who's the computer in kind of the, who is going to be computing on this data? What can you trust them to do? Can you trust them to compute what you want them to compute, and so on? And finally, who is this being used by? Like, who does get it? For example, like one of the popular scenarios that is used in motivating computing on encrypted data is like healthcare data, right? Hospital data. Here you have very clear distinction, like the owner is going to be the patient because it's their medical data, but the hospital holds it on their behalf, so they're going to be the provider. Typically, the hospital doesn't have a cloud infrastructure or a server room, or at least not of the right size, so they're not going to be computing on their own data. And also, if you want a large data set, you can't just have one hospital. That's not enough. That's not like statistically relevant. So you need to get more hospitals on board. And finally, who's going to get the output? Like, is it going to be a researcher? Is it going to be like a medical researcher? Is it going to be like a census person from the government trying to understand like health data and stuff like this? So these can be very different parties in certain scenarios. So now we get to like kind of the main part, and we go through different methods to actually achieve our goal. The first goal is to not encrypt the data, like the first, method. So either the data is just handed over to a third party that's kind of not part of the interested group of people, or the parties just share amongst themselves and then compute what they need to compute. So obviously there's no technological security behind this whatsoever. The private information of the providers and of the owners is just visible to whoever is doing anything. And then malicious parties can exploit it. You can compute something else, you can sell the data, whatever. You can put legal agreements in place to say, like, I don't allow you to do anything with my data. And this is basically how most of cloud computing happens today, right? A company uploads their customer database to, I don't know, AWS or Microsoft Azure or whatever. And there's just a legal agreement that Microsoft or Amazon will not, they'll just leave the data alone and they'll compute whatever the user asks them to compute, and they won't look at the result. And if something does go wrong and you find out about it, which is not a given, kind of the only remedy you have is a long and potentially expensive, well, if it's long, it's usually expensive, court case. And the best you get is like, what's the right word? Compensation. Like the privacy breach has happened. Too late. The information is out there. You can't take it back. The best you can get is compensation, which might not be satisfactory. The next step up is what's called the trusted execution environment. So also called TEEs. There's been a lot of talk about them because they've been around for a while, and sometimes referred to as confidential computing. So what you can do is you can, rather than storing your data in like plain text on the cloud, you can encrypt it, for example, symmetric key encryption. And then the cloud advertises the fact that they run a trusted execution environment. So they have these chips, like they had like Intel SGX and stuff like this, where essentially the computing unit has been hardened against outside observation. So when it stores data inside, you can't send commands to like make it pump out. So for example, it'll have like a secret key inside, you can't get that out. And as a data owner, you can like open a secure channel to the TEE, like an encrypted communication channel. You can give it the symmetric key for your data, and then it can like work for you on top of your data in the cloud, and your symmetric key stays within. And the kind of the metal server racks that are around this TEE don't get to see what's happening. They're just providing power, cooling, and stuff like that. But the thing is that side channel attacks, a bit like what Leonard was talking about just before, have been like demonstrated against such chips time and time again. So many of the iterations that the industry has produced have had some weaknesses identified. There's no evidence that any of these have been like deployed in practice and that like, customer or user data has ever been breached. But if you can do it in a lab, Amazon or Microsoft has the budget to do this. And so if you weren't trusting, the more security conscious person will say, if you're not trusting your cloud to not look at your data when it's in clear texts, how are you like, is it any better to trust them not to extract your key from their TEE if there is an academic way, if there's an academic paper that says you can do it? So it's slightly better. And if you're a company, paying for this might mean that you get to put a nicer sticker or have a better certification for your product, and it might be enough. But in terms of like kind of the cryptographic standard, it's still not satisfactory. So then we can start looking at slightly more mathematical ways of protecting data. One such thing is to do what's called federated computation. So this is a scenario where you've got kind of like multiple parties wanting to compute something together. So you're kind of back in the hospital analysis sort of scenario. And depending on what you want to compute, you can kind of like locally perform your part of the computation. And then you group together the individual parts to obtain a result or to continue processing further. So for example, if you want to compute the average age of 300 people, and each party has like 100 people in their data set, each party can compute kind of their local average, and then put that together and then average out the three things. And that works out, right? Mathematically, that gives you the same result as if you had taken the average. So depending on what you want to compute, you got to make sure you kind of split it in a way that recomputes the same thing. But then we can look at like what's the information leakage about this? Well, the local average of like each 100-person data set is leaked. Like maybe an individual average is enough, like it's going to be hidden enough. But let's say you had a fourth party who only had like 5 person in their cohort, things start to get like less certain. And also like this is like I'm showing you a one-time example, but usually the way like statistics works is like you can filter your data sets, right? You want to eliminate people that don't match or are going to be outliers or that you don't care about in your data set. So if you start enabling this to be kind of a query and response algorithm, then you can do smarter things in some sense. So for example, if you start saying, what's the average height of people that are older than 10 and then younger than 10? And then you say, what's the average height of people who are younger than 11 and like older than 11? And then you say, how many people are 11 in my data set? And then suddenly like, oh, there's 2 people. And then like you can kind of cross match the answers and you start finding out things. So if you take like, if you manage to partition your data set, 51 people on one side, 50 on the other, but like kind of the same 50 out of the 51, suddenly you can reveal individual information. So what needs to be introduced at this point is what's called differential privacy, which is that because this is a differential attack, you create a difference in the queries, like in the responses that you get, and you exploit this difference to recover the information. And so to do this, you add noise, and you want to add enough noise. For example, you add like imaginary people in your data set, right? Maybe like you know what an imaginary 10-year-old male is supposed to look like medically, and then you throw, like if you only have 2 of them in your data set, you add like 10 more fake ones, but like normal looking ones, to kind of hide the 2 that you have. Yeah. Yeah, this is exactly, add too much noise. If you add too many fake people, for example, in your data set, relative to the size of your data set, of course, then the quality of the data set deteriorates. So this is where there has to be careful calibration of how much noise you're going to introduce. And so kind of the idea is that, yeah, like each input kind of gets noisy, and then you can see that like, so not only the quality of the data set can deteriorate, but also like the quality of the computation, because you get more noise from individual participants. That noise kind of compounds when you start aggregating things. So the quality of your analysis is also likely to start deteriorating. So this differential privacy technique exists, but it requires kind of careful tuning to the specific calculation you're trying to do, to the specific scenario, to the specific data set, so that the quality is preserved. But nonetheless, it's an important one to remember, because it's about fuzzing what it is you can learn from the output of a query. Like, you'll see later that the next methods we're going to see, they're going to protect the computation while it's happening, but the output is going to be handed out to whoever requested it. So they will still learn the output as it was computed. So if you're making, like, let's say a query about 51 people, and you use like FHE or MPC, which we're going to talk about, and then another query about 50 people, like, yeah, the privacy of the data set's going to be preserved while that query is being computed. But when you, as the researcher, get the results, you can still do the differential attack. So differential privacy is it like, while it's more mathematical, like statistical, and not so much cryptographic, it still serves a role that other cryptographic techniques can't satisfy. But I'm going to come back to that. Okay, so talking about FHE, the next kind of method we have is homomorphic computation. And so you have a public key encryption scheme, and what homomorphic means is that if you're in like the ciphertext side of things on the left-hand side, you've got these encryptions of X and Y, you have this like round plus operation that exists, which lets you combine 2 ciphertexts into a single one. And the properties, like the mathematical properties of the encryption scheme, tell you that that ciphertext is going to be the encryption of X added with Y, whatever added with means. So if X and Y are floating point numbers, then the regular plus is floating point addition, but the round plus isn't going to be that, because your ciphertext, they're going to be bits, or they're going to be numbers in a large space or whatever. So then, once you have something like this, we can kind of look at our running example of computing averages a bit. So this time, we have to think even more about who's doing what. Which party, like the party with which role, is doing what operations in the protocol. So you see that we actually start with the output receiver, and they generate the key pair. And they're going to give the public key to the parties. And when they get the public keys, the providers, maybe on behalf of the owners, can encrypt their individual data into a ciphertext each, and then they can send it to the computing party. And then that computing party is going to evaluate. So in this case, for example, just computing the sum. And then that's going to be returned to the green party once more, the receiver, because they're the secret key, like they are the secret key holder who gets to decrypt and recover the data. So like this is a clear example where thinking about who owns what and who does what is very important. Because for example, if you combine the receiving party and the computing party, well then all the blue ones just send their data to someone who owns the secret key, right? If purple and green were the same, then you're not really getting any kind of security. Even though they might have promised not to use the secret key, you never know. Yeah. Okay, so that's for FHE, for homomorphic computation. The key point is that the receiving party has to be different from the computing party. Like one very simple scenario is like I'm a data owner. I can be my own provider, and I just want to use the cloud to compute something that I can't be bothered to do. I can be both the key owner and the data owner, right? I can encrypt my own data, send it off to the cloud, make them compute it in FHE. And at this point, I'm not trusting them to not look at the data. I know they can't because I'm the only one who knows the secret key. So like there's no TEE for them to kind of breach. They just have ciphertext that they can't make sense of. So all they have to do is compute what I asked them to compute, give the ciphertexts that contain the outputs back to me, and then I can locally decrypt that. So we have very fast and efficient linear homomorphic encryption schemes. So for example, like addition or averages, things like this can be computed very easily. For example, in electronic voting, all you're doing is kind of summing up votes and stuff like this. So you don't really need very fancy homomorphic encryption for that. But nonlinear functions such as standard deviations, so for medical analysis or any kind of statistical analysis, that's very interesting. Also, for example, large language, like machine model training, you usually need to compute, and also inference, you need to compute activation functions. These tend to be highly nonlinear. So these kind of require what's called fully homomorphic encryption, so FHE, and I do believe you'll have more talks a bit about this during the rest of the course. But essentially FHE, so the first line is what we had, kind of additive. FHE also lets you do multiplication. So you can do both of these operations, and then computer science tells you that if you can add and multiply, you can compute whatever you want to compute. But this comes with kind of more cryptographic baggage, because being able to do both on the same encryption scheme was a long-standing open problem until the early 2010s, I believe. But the last kind of 15 years has seen quite a lot of progress. So for MPC, MPC, which stands for multi-party computation, it achieves the same goal, which is to evaluate a function, like a statistical analysis or a SQL query or whatever, evaluate this function on private data. But rather than having a single computing party that handles ciphertexts, we're going to use multiple parties that are going to talk to each other. And these parties, for example, could be the data owners themselves, or the data owners or the providers can kind of give their data to someone on their behalf. And the security then comes from the fact that we use multiple parties. So there's no like an encryption scheme that we're going to choose, which is going to provide confidentiality. The idea is that usually we're going to split the data across the parties so that the individual parties cannot recover enough information. But then you get into a scenario where if too many parties collude and like exchange the information that they're not supposed to exchange with each other, you could lose the security, potentially completely. They can recover all of the private data. So you have to make an assumption when you deploy MPC. You have to say, okay, I'm going to deploy MPC with these 5 parties, like let's say these 5 different hospitals, and I'm going to assume that like no more than 3 of them would ever kind of come together to share their data and recover the information. I can tolerate if 2 or 3 of them try to do this, but more than that, and my protocol doesn't give any guarantees anymore. You can configure it so that like you would need 5 of them to configure. That's kind of it's a parameter you can choose, and it kind of decides how expensive your MPC protocol is going to be. But in some cases, if you are one of the computing parties, you can kind of trust yourself not to collude with anyone. And if you've chosen the right kind of MPC protocol, your security is going to be guaranteed. So yeah, to give a bit of more concrete of the thing, more concrete kind of representation of how this computation works, each data element, whatever that, whether that is an integer or some other representation, and we can split it. So what we'll do is we'll choose like x1 and x2 completely at random in some space, and then we'll set x3 so that the sum is equal to the data point, and then we're going to give one piece of these to each party. So it could be like one of the parties who owns X creates this sharing and gives like 2 shares to the others and keeps 1 for itself. But you could imagine something like a mobile phone that owns X creating the sharing locally and then giving X1, X2, X3 to 3 different servers that are going to do this. So this is where kind of like the data owner, provider distinction with the data, like the computing parties, is still relevant. Because like you can kind of see that if we have a sharing of X like this and a sharing of another value Y, then like adding the shares together becomes a sharing of the addition of X and Y. So again, computing linear function is like local. You can just add your shares together locally. You don't need to talk to the other parties. But if you were to multiply a sharing of X and a sharing of Y, you start seeing things like X1 times X2, X3 times X1, and stuff like this. So, sorry, X1 times Y2, X3 times Y1. And for these, like, individual parties don't have enough information to do this. So you require interaction when you want to start doing nonlinear things such as multiplications. And that's kind of the big thing to remember about MPC, is that it takes a lot of interaction while the computation is taking place. Yeah, so to kind of exemplify this a little bit, you can someone has a secret, a data owner, they can create the sharing of it and distribute it to the parties. Then the parties are going to interact with each other several times to compute the function. And finally, they can recombine their shares of the output so that whoever gets all the shares can recreate. So again, here there's a lot of flexibility to decide who gets the shares. You can send different output to the different parties. You can send the one output to a third party that's been identified. Very flexible at this stage. So to kind of compare FHE and MPC, which at the moment are kind of like the really big competing, well, not competing, but they are the kind of the 2 major cryptographic techniques for secure computation on confidential data. FHE doesn't require a lot of communication because like once you've sent the ciphertexts of the inputs, they don't need to leave wherever they're being kept. All computation can happen locally, but it is a lot of computation that needs to happen because the encryption kind of adds a lot of overhead. And also the way that FHE typically works is you encrypt, and then like when you are encrypting, you're adding noise to kind of fuzz your plain text within the encryption. And then when you start combining ciphertexts during your operations, the noise you added starts combining as well. And so when you're just adding, the noise kind of stays manageable. But if you start multiplying things, that noise can grow. And if you don't get rid of it somehow, it's going to end up kind of overwriting the data within your encryption. So in FHE, there's a step called bootstrapping, which is kind of like decrypting to remove the noise and re-encrypting with like fresh, lower amount of noise. But you need to do that in encrypted form because the server that is doing the computation can't decrypt locally. It doesn't have the key. And if it had to send it back to you for you to decrypt and re-encrypt, you would be doing that so often anyway that it wouldn't be very practical. In contrast, MPC doesn't use encryption. It's not even noisy encryption like FHE does. So there is very little computation comparatively to do. However, because you have to communicate at every nonlinear step of your circuit, like the computing parties are doing this very often. So you need to make sure that you have like, gigabits or even more bandwidth like links and speed between the computing parties, because like if you're saying you want to be super secure and have like one MPC party in North America, one in Africa, one in Australasia, your computation time is going to grow hugely just because of the network delay. So in that sense, these kind of very practical consideration can show up in the feasibility of an application. So when I first wrote those slides, that was true, but that was a couple years ago. So maybe someone will prove me wrong by the end of the week. But MPC tended to be faster than FHE because you can make, like, we engineers know how to make communication fast, and MPC has very little computation. But researchers and engineers have been working at making FHE computation fast. And the real progress for this has happened in the last 3 to 5 years, maybe. And so MPC still had the edge until recently. And you can do relatively complex functions relatively fast, but the problem is this multiple parties requirement. Because if you think about it, we always like to sell MPC as like, yes, you can have multiple hospitals and stuff like this. But at the end of the day, if you're trying to have a business model for your application, like you need to find this configuration time and time again. Every kind of customer you want to sell to has to be multiple parties in some way, which something like which can be hard to find sometimes. Like if you require competitors to agree with each other and like participate in this, it's kind of like, well, why would they sign up to something that kind of enables their competitor to also get the advantage of like shared data analysis? So this is why we usually see things like hospital medical data analysis, or for example, like government census. You can have like individual government instances, like institutions maintain their own database, and then you can compute aggregate statistics over like financial data and education data and healthcare data and like benefits data without having to actually merge these databases, which is typically prohibited by laws and like data protection things. Also, like the parties have to be distinct, right? If you're just running 2 MPC parties in like the same Amazon instance, are you really distributing your computation enough? Yes? Mm-hmm. Mm-hmm. Well, yes. If you have a centralized database of medical data, it takes one breach for multiple countries or hospitals worth of data to be leaked. Also, like, without, if your hospital leaks your data, you can blame them. But if they gave their data to someone else and they leak your data, like, it gets even, the chain gets longer. Actually, your question reminds me that there was an effort to have like a European sort of MPC-based solution where there would be a framework and you can set up instances and data providers kind of essentially share their piece of their database into this virtual pie. But the data would never actually leave the individual things. And you could do this like at the country level or at like medical institutions and stuff like this, yeah. Yeah. And so this is why the last comment says that like, yeah, MPC is usually, they usually like, it's very hard to, it's not hard, but it's been a bit tricky to find applicable scenarios where MPC really is the solution that you need to solve the problem. But it exists and it has happened in practice. Another scenario in which MPC has been useful is when you have like a single point of failure for something in your application and you want to remove that. So for example, banks typically, banks once a day, they send a lot of money to each other, right? Like rather than have, whenever you make an individual transfer to bank B from your bank A, but someone else in bank B might make another transfer to bank A, right? So once a day, there's this like clearing procedure of how much each bank owes to which other bank, and they just send all the money all at once. These need to be authenticated. These need to be signed. So if you control the signing key that sends millions of euros a day, you can do a lot of financial crime. And at the end of the day, we can say the bank controls the key, but at the end of the day, it sits in like one HSM somewhere in one building. And so there's like all kinds of protections that I don't know much about to make sure these keys don't leak. But at the end of the day, that's still a single point of failure. And so in the last 10 years or so, there's been more and more solutions where you can say, well, rather than have one secret key in one place, why not have 3 or 4 or 5 servers across different locations that the bank, where the bank practices, and they can each hold like a piece of the secret key. And as long as like, let's say 3 out of the 5 pieces come together, you can compute that signature which authorizes the transaction. So if you deploy this, then an attacker would need to breach 3 of your locations rather than 1 to get your secret key material. And the other thing that kind of, if you're going to do this only once a day, back in the days, like this was kind of an expensive or a slow MPC computation to do. But if you only have to do it once a day, it doesn't really matter if you need to like start it 2 hours before the time you actually need to send off the signature. Nowadays, computing such a signature takes milliseconds between well-connected parties. But you can imagine doing bigger and bigger computation in kind of the same way. So that's kind of a second track of applications for MPC, which is where like you have a single point of failure. You don't want to merge, like you have a piece of data that's very sensitive, or you have distributed databases that you don't want to group back together, but like it's still all under your control. So you can deploy MPC not like as a privacy preserving solution, because like you're the owner of everything. So the privacy is not really relevant to you, but it is a form of kind of like security from distribution in some sense. So this is the slide about what I was talking about with differential privacy. MPC and FHE will protect the inputs and like the computation while it's happening only until the point of what can be learned from the output, right? If I say to someone, hey, let's compute the average of our salaries using this MPC box, well, if it's just 2 salaries and I know mine, I get the average, I know yours. So it's not really useful. And so this is where you can add this kind of like noisy data into the system before it gets input into these privacy-preserving computation technologies to kind of prevent any kind of differential information leakage. But like the noise, it's not necessarily trivial how to do this. You have to kind of pay attention to how the systems get integrated, where does the noise get added, who knows the noise, who gets added, because if one party knows all the noise, they can maybe remove it afterwards, even if it's gone through some kind of computation. So it's not straightforward, but it does like serve a different role than what MPC and FHE will do. Then we have to consider active attacks. So what I mean by this is that up until now, we've been talking about passive attacks. Like a passive attack is like some data stream kind of comes in front of your eyes and you're looking at it. And if you can't make any sense of it, you just do whatever you're supposed to do and then you pass it on. But especially with FHE, you have to consider the computing party and the power that they have. Because all they do is they take some ciphertext in, compute, and then return a result. You don't know what they've computed, technically. It's a bit like, I mean, we all trust our CPUs to execute the program we ask them to execute. But under the hood, like you're not looking over the shoulder of your CPU checking that they're executing every single instruction the right way. And the thing with an FHE, that's kind of the same thing. The cloud that does your FHE computation for you could compute something else. And this is what we call an active attacker. And then, you know, you could be wondering like, well, what's the goal of this, right? They just give me something else. Now I see like a wrong, you know, I receive an output, but I have no way of checking whether it's the right one or the wrong one. Like, how do I know that if I get like 25 as my answer when it should have been 27, how can I detect this? So that's one thing. You can just not be able to detect that. Another is they might be able to, you know, create an error in the computation. So they send you a result and then you see that it's wrong and you say, hang on, that's not right. Like, do it again or change. And the thing is, if they know what they did to make it return an error, that can be data dependent. So they're like, if your data was this, my action will cause an error. But if your data was that, my action will not cause an error. So depending on the user's response at the end, they've learned something about your data because of how the computation was kind of structured. So that's another thing to think about, is like, what computation are you asking them to do? And could it have these kind of like data dependent control paths and error things? But in MPC, so like FHE, you send off the ciphertext, it starts the computation, and you have no way of controlling what it's doing until maybe at the end. In MPC, because you have to interact at every single nonlinear operation, you require the consent of the computing parties at every moment. So if someone tries to change the instructions that the MPC computation is doing, the honest parties, the ones that the attacker does not control, they'll be like, hang on, something's not right. The others are trying to compute something else. So they can just withhold their share of the data, and then that just blocks the computation completely. So in MPC, you can prevent this kind of malicious behavior. And the state of the art for this is what we call active security with abort. Because if you're happy with, if you're satisfied with the eventuality that your computation just aborts with no useful output, if this kind of behavior is detected, then you maintain security. So to be able to secure FHE against these kind of active attacks, we need kind of a third area of technology. And these are usually referred to as verifiable computation and also zero-knowledge proofs. So that's kind of the problem summarized. If we've asked someone to compute something for us, how are we sure that they've done it correctly? And verifiable computation and zero-knowledge proofs are kind of two related ways of doing that. It's usually called verifiable computation when there's no secret information, right? So if you've asked a server to do some FHE computation for you, they don't have any secrets. Because you know which ciphertext you've given them, they just need to run through the thing. Zero-knowledge proofs is when the person that is computing has something to hide or to keep private. And so it's usually a little bit trickier to give a good example of what that looks like. But essentially, like, imagine a scenario where like the FHE gets stuck in the computation somewhere and asks you to help them with your knowledge of the secret key, and then like give them something back to continue. And they want to make sure that when you help them, when you compute that, you're computing the right thing. You're not kind of inducing them into another path or something else. Then you would give a zero-knowledge proof to say, I computed what you wanted with my knowledge of the secret key, but the assurance that you're giving doesn't leak anything about the secret key. So the server is convinced you did what they asked them to, what they asked them you to, but you're not. Your privacy is kind of maintained. Another example where where ZKP is useful is, let's say you want to do machine learning inference, right? And like some companies spent a lot of time and money acquiring a data set. They've trained a machine learning model on that data set, whether it's for, X-ray analysis or whatever. And now you've got a query for that model that you want to run inference on. They can't just give you the model, because at that point their competitive advantage just disappears and you can take their model and run it yourself forever. So what they can do is they can commit to the model, like they publish like a hash of the model, or saying this is the model that we trained, or like this is a fingerprint of the model that we trained, and we are promising that when you send us a query, we will execute it with that model. And so when you send them the query, and for now we don't have to think about the privacy of that, they will run inference, but they can at the same time give you a proof that they executed the inference against, like, with the same model that was publicly committed to. So they're not revealing the model, but within the proof they kind of recompute the commitment, or they verify the commitment. And so when you get your result back with that proof, you are cryptographically guaranteed that they use the same model. And so you can be kind of reassured that when you paid them what you paid them to run the inference, you really got what you paid for. Of course, if you want the privacy of your query, you can do all of this in FHE. You encrypt your query under the FHE scheme. They execute the inference as an FHE computation, and at the same time give you a proof that they executed the thing. And one kind of key requirement is usually that verifying the proof should be faster than generating it, because otherwise it kind of tends to not have as much purpose. Okay, so I'm gonna take like kind of a few more minutes to go over this, and then we'll have a few more minutes for questions, because it's 2 minutes to the coffee break and I don't want to deprive you. So for FHE and challenges, and take all of this with a grain of salt because I am not an FHE expert. So if I make promises that turn out not to be true, I'm sorry, and someone will correct me again, probably later this week. Nowadays, like, individual operations are getting really fast on CPU. Not like clear text fast, not as fast as like one CPU instructions where you can do billions in 1 second, but they're getting quite fast. The problem is that what we want to compute in FHE is quite large usually. There's a lot of operations. So overall things still take time. But this bootstrapping operation I've been talking about has been implementing on GPU. There's a lot of works, including from people at COSIC or who used to be at COSIC, to do kind of hardware accelerators, so like FPGAs and ASICs for FHE relevant operations. There's a lot of open libraries. So for example, OpenFHE or TFHERS, which are available online and maintained to kind of enable people to build on top of FHE, which is nice. And many companies in the space are deploying products. Some of the challenges that kind of are still a bit relevant, the size of the ciphertext, like that's still kind of big relative to the data that it actually encrypts. So you get kind of bloat in when you're doing the computation. Bootstrapping time, but that's being worked on really hard, and like handling multiple users. So that's something where I haven't really talked about, but what if you want to do an FHE scenario where like multiple different receivers each kind of need their own public key? Like the algorithms, the initial cryptographic algorithms that enabled FHE weren't really meant for this. You just had one key. So how do you handle the scenario where you want more than one? For MPC, active with the board protocols are really fast. For example, like distributed ECDSA signatures takes like less than 100 milliseconds, especially if you have like only two parties. You can do maliciously secure inference also, like with March. So like we have this kind of malicious versus semi-honest, which is kind of active versus passive security. And usually active security had quite a high overhead. And now this overhead is thinning, but it's still more expensive than just running it in the clear. One of the problems with MPC is representing and operating real numbers. Like floating point precision is kind of difficult to handle, because like you need to kind of remember how many decimal places and these kind of things, and handling all of that within the MPC privacy preserving mechanisms is difficult. Iterative methods, like if you want to iterate something until your error is small enough, but your error is encrypted, how do you know when to stop? And that's also a problem with FHE. Like, how do you know when you've iterated enough? You can do like kind of fixed length. You can say I should converge within 50 iterations, but I'll do 200 just in case I don't. Because like if I stop, ask the user, has this converged yet? Get an answer back, then I might learn something, because I might learn that certain pieces of data don't converge quickly and others do. And so you can leak information in that way. Also popularizing the tools for non-expert users to kind of configure, deploy MPC. That's still hard. There's a whole like, there's some libraries out there, but usually it's like special purpose implementations that are hard to configure. For zero-knowledge proof, there's now this thing called snarks, which can prove arbitrary computation. A very big driver of zero-knowledge proofs in the recent years has been blockchain applications, because in blockchains, computation is expensive. If you want the chain to compute something for you, you've got to pay for it, because it's like validators across the network replicating this. So usually what you would want to do is you want to make a large computation. And if you want to say, well, the chain approves, you need to give a proof of this that gets verified by the chain. And then the chain like it's cheaper to verify the proof on the chain because it's less computation than what you did. But you have kind of the cryptography tells you that if the proof is valid, then the computation was done correctly, and so on. So there's been a huge drive from there. You can prove like blockchain transactions in like less than a second, for example, and stuff like this. And now people are like shifting towards proving much larger things like machine learning model executions and things like this. And actually like the Ethereum Foundation is now working on a big project where they want each block of the Ethereum chain, which happens once every 12 seconds, to be proven in zero knowledge in one of those proof systems, like before the next block. So like in 12 seconds, you've essentially proven the entire state update of the Ethereum ecosystem that the block decided. And I think we're at the stage where like maybe some proving systems are doing like 98, 99% what they call real-time proving. So as the Ethereum chain advances, there's like a provable guarantees that it has advanced correctly, kind of without the kind of the replicated system of validators. But yeah, so all of this works on like in the arithmetic world, which brings a lot of overhead, and business applications, like genuine business applications, although Web3 people will tell you blockchain is genuine, but kind of slightly more society relevant applications of zero knowledge proof is still a bit harder to find. But they're showing up, like, for example, in like the EID wallets and these kind of things that like Google and the European Union are trying to do, where you can give like proofs of credentials. So, you know, you want to be able to prove to a business that you are older than a certain age or that your postcode is in a certain area. You have like a government issue digital identity on your phone. And you don't want to show it to them, you can like generate zero knowledge proofs that your identity matches the criteria, and the merchant's terminal just verifies this. And so you haven't had to give them your data, and they'll only know that you live within a certain area or that you are above a certain age, and they'll learn nothing else about you. So it's slowly showing up in these kind of areas, but like in commercialization is still a bit difficult. Yeah, and I'll stop here because the use cases, I think it's not very valuable to go over now that you have kind of the big concepts, but feel free to look through them afterwards, and my email is on the first slide. So ask me questions if you have any, and do you have any for me right now?